I will start with explaining all these buzzwords one by one. So maybe I will first start with the model, so the preferential attachment type model. And I'm doing random graphs here now, so a little bit different than the talks before. So what are we dealing with here? We're looking here at preferential attachment random graph models, and this is like a model philosophy to build a random graph. And the idea goes as follows. It's a dynamical model, meaning that new vertices arrive one by one to the system. And when a new vertex arrives to the existing graph, it tries to connect to each existing vertex with a certain probability. And it has a preference for powerful vertices. Now it's in our modeling task to decide what does powerful mean. So in more classical preferential attachment models, the powerful vertex, or the power of a vertex, can be measured by its current degree. This is a pretty interesting model, but it's also a little bit complicated when the probabilities depend on the current degree, which are itself random, lead to a lot of dependencies and hard analysis. So our idea is I will now introduce the random graph model, which still follows this preferential attachment idea, but will be simpler, like a toy model. We will get then we can do actual analysis on this, and on some day, I hope we can extend it to the more general models. So maybe one word, why is it interesting to study such preferential attachment models? The cool part is, if you look into them and you just build a model with this preferential attachment idea, these models usually will have a lot of very interesting properties, like the ultra small world property, meaning that the graph distance are typically very, very small, or the asymptotic degree sequence follows the power law, and there are many more interesting properties of random graphs. And how do I decide when a property is interesting? If you look at real-life large networks, like, for example, the World Wide Web network, or like some social network like Facebook, and observe this non-random network, you will statistically find these effects I just described. So this is a random model which omits a lot of effects, which has a lot of effects which you can find in real-life networks. So that's why we are studying it. And now I will give you a simpler idea, or introduce our model of this type. So the idea goes as follows. It's still a dynamical model, and when a new vertex n arrives to all earlier vertices from 1 to n-1, it tries to connect to each of these vertices independently of each other with a probability proportional to m to the power of minus gamma. And gamma is a parameter which we can play around. And this gives us this preferential attachment effect. So it will prefer vertices with a low index. So it prefers vertices which are in the system for a long time, then the probability of connection will be higher. And for older vertices, for newer vertices, this will be lower. So these are the early vertices are the powerful vertices in this model. So one thing we have to note here, if we do it like this, we can try to calculate the expected degree of this new arrived vertex n. And since all the connection probabilities are independent of each other, it's just the sum of Bernoullis, and the probability will be proportional to the sum, and the probability was proportional to n to the power of minus gamma. And then you can calculate this, and it will behave like n to the power of 1 minus gamma, which explodes if we send n to infinity. So one more part I have to do in this model is we're usually only interested in sparse random graph models, meaning we don't have too many edges in the graph. So to make this model sparse, we have to choose to proportionally factor in the probability I just gave you to be of this order n to the gamma minus 1. So we have to divide by what we just got here. Then this random graph model will be sparse as well. So, and all of this together gives us like this formal definition now. Okay, we work on the vertex set from 1 to n, denoted Vn, and the connection probabilities of the probability of two distinct vertices I and j is given, they will connect to each other with the probability Pij, and this is the full connection probability, is given by beta, some parameter, times the maximum of I and j to the power of gamma minus 1, which we just derived to make the model sparse. And then I times I, the minimum of I and j to the power of minus gamma. And this is the preferential attachment effect. This is like our full model. And we have two parameters with we can play around with. Gamma parameterizes the strength of the preferential attachment effect. So how strong do we prefer the early vertices in the graph? And beta just artificially increases or decreases the connection probability for all vertices, which we call the edge density parameter. So this is the vertex. This explains the first buzzword, the inhomogeneous random graph of preferential attachment type. Because if you do it like this actually falls in a large class of random graphs, the inhomogeneous random graphs, which are very well studied, and there are a lot of examples of this. I think we have later today a talk about the stochastic block model, which also falls in the class of inhomogeneous random graphs. Yeah, so this is this. But now we work on the subcritical regime. So I have to explain what is this and what this means in our case. And I want to cite this following theorem. So in this inhomogeneous random graph model, or in the model I just presented you, there exists a giant component, meaning that the size of the largest component of this network is of order n, if and only if the parameter gamma is bigger than 1/2, and then we are in a robust case, or beta is bigger than beta critical, which depends on gamma. So, and I don't want to go into the proof, but Peter Mörters, my advisor, and Stefan Derreich had a paper together in 2013 where I proved a similar result for this for the more general preferential attachment model. And you can adapt the proof and get this result for the simpler model. So nothing, this is this. But from now on, I will be working in the subcritical regime, meaning that gamma will be less than 1/2 and beta will be less than beta critical. So this is now, this explains the subcritical part. This means we have the largest component is, or there is no component of order n, they are smaller. Good. Now we know the model, now we work in the subcritical regime, and now I can show you like my main result, which we were able to prove quite long. We will go through it slowly. Little bit of notation. So with Sn of I denote, or we denote the size of the connected component of a vertex in our graph. We were, like I said before, we work in the subcritical regime. And now we take a sequence of vertices On, such that On divided by n converges to some u. This just means we look at the growing sequences of vertices which grow in a typical manner. You can think of On as u times n. Maybe you have to floor it or something. But we just look at a typical sequence of vertices. We can't look at a fixed one. And then we have the following limiting result. So we go through it slowly. If we look at the size of the connected component of these typical vertices On and scale the size by u to the power of rho minus, and rho minus is an explicit constant which we can calculate in terms of gamma and beta. It's just nice to know that we know it explicitly. And if we look at this size of the connected component and first send n to infinity, so we're looking at this in the graph limit, and then let u go to 0, so we're looking at the size of the connected component of early typical vertices where this u gets smaller, then this converges, or then in distribution to some random variable w, And the nice part is we also know, or we can identify the asymptotic tails of this random variable w. Like this is the main result. So this explains the title. We know in our preferential attachment model here, we get an asymptotic result about the size of early typical vertices, about the size of the connected component of early typical vertices in this graph. This for itself is quite nice. And maybe just the more natural question would be, okay, we'll work in the subcritical regime. We know there is the biggest component is not of order n, but how big is the biggest subcritical component? And this is a very hard question. And this is what we are currently trying to do. And hopefully this is the important intermediate step, which gives us the result. but identifying the size of the connected components of early typical vertices should be helpful. So this is the main result. And with the bit of time I have left, I will go a bit into the proof. And you can separate the proof in two distinct steps. Like we will first look at this connected component of this vertex ON, and we'll couple it to a killed branching random walk. And this is what I will show you mostly in pictures. And if you manage to couple the connected component to a killed branching random walk, then you can, in the second step, or to get the outer, to prove the outer limit, you will use some results on killed branching random walk theory. But step by step, I hope this wasn't too much. So the part I will show you or go through briefly is this first proposition for the inner limit we are following theorem. If we look at the sequence of typical vertices in our graph, then the size of the connected component of these typical vertices converges in distribution to the number of particles in a killed branching random walk. And we achieve this result by coupling the connected component to a certain killed branching random walk. So to explain this, maybe I introduce what the killed branching random walk is, or what this was. And I think this picture explains this pretty well. A branching random walk is defined as follows. It starts at some position, at some root, which can be random or deterministic. In our case, it's log U, so not random. And the killed branching random walk is defined as follows. We have a Poisson point process. In our case, we know it explicitly. And this Poisson point process generates the displacements of the children of the root. So in our case, the point process generates these 4 points, which are all on one height. I try my best to point them out. And then you repeat this process for all generations in an independent manner, meaning in a given generation, you look at the particles in a generation, for example, this one, and then you take an independent copy of this Poisson process, which generates you the offspring of this particle. And you do this for all particles in a given generation, and you try to do this forever until the process dies, or it can live forever. Like this depends. But we're looking at killed branching random walks, meaning, and in our case, the killing barrier is 0. If a particle gets ever over the position 0, we will kill it, meaning it's not part of this tree anymore, and it's not allowed to produce any offspring. This is the killed branching random walk, or the branching random walk with killing, with this Poisson, with the intensity of the Poisson point process given by this expression. Just noteworthy here, if you look at the positive part, this thing explodes if we send y, let y be bigger. So we have infinite offspring to the right, but since we're killing in 0, this isn't a problem. And you can actually prove, but this is just branching random walk theory, that this process becomes extinct after a finite number of generation in the subcritical phase. So for the same parameters like in our model. So it's very closely related. So now I want to couple the connected component of this typical vertex in my graph with this particular killed branching random walk. We have first to notice that if I explore the connected component in my graph, it will have with high probability a tree-like structure. So the probability that cycles are built is very low. So I want to couple, in other words, I want to couple a tree with labels from 1 to n. This is the connected component of my graph with this killed branching random walk where the particles have labels on the negative real line. So the question is, how do you do this? For this, to achieve this coupling, we define, we have the following map, phi n, which maps these labels from 1 to n from our graph to positions on the negative half axis with this function. And where the I is here down in the summand. And just notice that the youngest vertex, so the vertex n, will be placed to the origin, and the older, powerful vertices will be placed to the left, but with decreasing intensity because the summands get smaller. So, yeah. And observe that typical vertices or the strong and the typical vertices will be placed to the left. The typical vertices with high index will be placed to the left, and the strong vertices will be placed to the right. But the question now is, okay, I mapped the labels from 1 to n to the negative half line. How is the coupling defined? I think I just explained it in the picture. The killed branching random walk could look like this. We start with a particle here. This would be log u. If a particle gets above 0, it gets killed. If it goes below or stays in the negative half line, it could look like this. And it's position t. And the coupling is defined as follow now. I want to project the particle with position t to the label I if the position t is between this map phi n of I and phi n of I plus 1. So this gives every particle with a certain position, maps it to a label between 1 and n. And this works out if we send n to infinity, because this map phi n behaves for n to infinity like minus log n, and it will cover all of the negative half axis. And then the natural question is, okay, I get this coupling, I map labels from 1 to n to these positions. What can fail? And this coupling will fail if following happens. If we have two particles which land in the same region, like here, then both of them would be projected to the label I in the graph, or in the tree-like neighborhood of the graph. But this is impossible. The labels are unique in our graph. So we have to control the error probability of that. And just want to say in words why this works. There are two effects which are taking place. I want that this coupling works with high probability. So it should work when I send n to infinity. And the thing is the following. What I actually have to do if I want to calculate this is, okay, the number of particles which will be projected to a certain region is just the Poisson number of points which lands in the interval such this. This is just a Poisson random variable with intensity given by the intensity I gave you of this interval. This is, you can calculate this explicitly. We have everything explicitly, and you will want to couple this Poisson random variable to the Bernoulli random variable of our random graph, and the probabilities were given by the PIJs in our model. So it's just the principal task of coupling a Bernoulli random variable with a Poisson, but we have to do it for a lot of cases and distinguish some cases. But why does this actually work? If we send n to infinity first, this interval where a particle will be projected will shrink just by the definition of the map, which decreases the Poisson parameter. And if we send n to infinity, this projection interval will also shift to the left, which also by our intensity, or this also shrinks the Poisson parameter. And these two effects combined allow us to actually, there are quite some calculations, but these are the main effects which allow us to actually couple this Poisson offspring of the projected tree with the Bernoulli offspring of our tree-like neighborhood of the graph. And this is the main ingredient of this first proof. And then we have that there actually exists a coupling such this tree coincides with the connected component of a typical vertex with high probability. So the connected component actually looks like a tree in the graph limit, and we can couple it to this certain killed branching random walk. This is like one of the main ingredients here. And now I just want to give you, this is my last slide. I just want to finish this up.
We didn't let you start until a few minutes late. So don't.
Okay. Then we just go with time through the last slide. So like now we saw, okay, with high probability I can couple the connected component to this certain killed branching random walk. And from now on, we only have to do use theory about killed branching random walks. And the proposition for the outer limit, which then together with the inner limit proves my whole theorem, reads as follows. You just have that if you look at the T of U, it was the number of particles in the killed branching random walk. And if you scale this number of alive particles with U to the power of rho minus and then send U to 0, then this will converge to this random variable W I promised you in the main theorem, in distribution, if I write it like this. And this random variable W actually also has this asymptotic tails. I don't want to go into the proof, but the idea of this proof is based on a paper on killed branching random works and work of Idecon and two other authors. And the idea is just there's a remarkable, amazing paper from the 80s from Ole Nerman, who, and under certain technical conditions, you get convergence of particles alive in the killed branching process. And we have the idea from here, and then we try to apply this to our case. You just have to relabel stuff and shift stuff and prove or check a lot of technical conditions, and then you get this outer limit. But it's just killed branching random theory, killed branching random walk theory. That's why I didn't want to go into it. And with these two together, this proves the main theorem. This is all I wanted to show you for today. Thank you.
Thank you. Do we have questions? I see. I was going to try the back. I was going to go to the back if there was somebody in the back.
Oh, sorry. No, but you can go to the other.
I could go to the back.
Okay. Can you walk fast? Yeah, okay. Yeah, so you have these components in the subcritical case.
Yeah.
Most components are trees, right? Or
Yeah. If you look at the component of these typical vertices,
yeah,
then it's
and you know how many components have cycles? Like how many cycles there are?
That's a good. And I don't know.
Okay.
Like, but if like what we did was, if you look at the components of these typical vertices,
yeah,
like how they defined them, then with high probabilities there are no cycles.
Yeah.
So you have to look somewhere else. But I never tried to.
Okay. Thank you.
Thank you.
Now I get to run up to the back.
Yeah.
Did you take your pills? Yep. Yeah, we have to worry about that, Luke.
Standing by.
Oh, sure. Yeah. I'd forgotten where I was going. Yeah. It was the hair color.
Yes. Okay, so all this was about typical vertices, as you said, but as a contrast, you know what happens if you start with a atypical vertex? I mean, the extreme case would be to look at a component of vertex number 1.
Yes.
Do you know how big that is?
No, but we have our tools, or the tools I derived here, don't allow to do this directly, but I have a hypothetical assumption.
Mm-hmm.
Maybe I show what I didn't manage to show. So we have some heuristics how the largest subcritical component would behave, which has something to do with you just asked. Namely, if you allow me, which is not allowed in my theorem, I first have to send n to infinity and then u to 0. Otherwise, the proof won't work. But if you allow me for the moment to let n and u to go to infinity and respectively 0 simultaneously, then it would be allowed to look at u something like c divided by n or 1 divided by n. And then you could, in this hypothetical theorem, look at the size of the connected component of the vertex with label number 1. And if you do this in this theorem, this would yield that the vertex and the connected component which contains vertex number 1 is very likely to be the biggest subcritical component. And this would yield to our hypothesis that the largest subcritical component is actually of size n to the rho minus, and rho minus is the constant I derived earlier, which is bigger than gamma. So it would be significantly bigger than in other models of rank 1 type, or you did some work on preferential attachment with a degree sequence, right?
Well,
yeah, you also.
Yes, I done work with on inhomogeneous general graphs in general, but not covering your results here. Okay. No, that's why I'm curious to see what happens.
Yeah.
Yes.
Yeah, here gamma.
Okay. But I see it's still work for the future.
Yeah, that's what
Okay.
this what I showed you here is of course not allowed, but I
No.
try to extend this theorem to allow to look at the size of component of vertex number 1
Yes.
with the goal to get the biggest subcritical component.
Yes. Okay,
This,
thanks.
This is then my hypothesis. Good.
Other questions? As long as it's Luke not asking the question, I can actually tell if anybody's got their hand up. Okay, thank you very much.
Thank you.